Hello, welcome and good evening to the next episode of Let's Code MS-DOS. And today we will return to the question of how to put stuff on the screen. We're still working on the game, and to make the game nice, we need to be able to support something like sprites. Sprites are moving objects on the screen, like little rectangles with graphics data that we want to push around for our player character or whatever assets we have. And we are not very performant at the moment in doing that in Mode X. I've got our example program here. I changed it a little bit so that we load 4 GIF files. And I actually opened 2 DOSBox windows here because running this program from within TurboC leaves not enough space for the actual program to load all 4 GIFs. It's a bit wasteful at the moment, but that's how it is. So I've got a second screen over there where I will run all the programs. Anyway, we just simply load the programs, and if any of those is null, it says couldn't load image, but it won't happen. Then you switch to the graphics mode, set the palette, and then we cycle through the images, but not as we did in the page flipping tutorial, because we want to simulate now what happens if we want to create a dynamic scene from memory, putting stuff from memory into the VGA. And we do this by the function called copy to page, which we already did program in a previous episode. It takes some image data, which was loaded from the GIF file, and copies it to the back buffer, basically. VGA page 1 is always the back buffer, because the page flip function will flip buffer 0 and buffer 1. So this will be copied in the background so you don't see any screen tearing, and it will just be copied to the top left corner with the width and height of the image. And these are just full screen images, 320 by 240, no, by 200 actually. Then we increase the frame counter, and then we delay by 1/4 of a second, but I can even take this out and it will still be very slow. This is just for the optimized version that we're doing now later, so that we have roughly 4 frames per second, because this is just a 4-frame animation. And a very cheap one at that. I just doodled it on my iPad. So when we run this, and using our copy to page routine, it loads the 4 images, and then it swaps the images very slowly. This is not 4 frames per second, this is slower. This is more like 1 frame per second. So our copy to page routine is extremely slow. And we can have a look at why that is actually. And the main reason, if we go here, let's see where copy to pages. It's not in GIF. It is in VGA.c. Yeah, and it's somewhere further up. Here we are. Copy to page. It's a very simple procedure. It goes over the y and x direction, and then it reads out the value at the source image and uses setPix to actually set it in the Mode X VGA in the given page. And setPix is slow because setPix makes 2 output calls to the VGA to select the correct plane. Even if we are already selecting the correct plane, we still do the output. This is horrendously slow. One optimization would be to actually store here in a static variable which plane we selected last. But the problem is you might have some different calls that change the plane. And then you're back to square zero and you still have to do this stuff. So port calls are extremely expensive. This makes everything super slow. That and the fact that we can only write 1 byte at a time here and not multiple bytes, because at least on the 286 we can even write 2 bytes at one time. On 386 we can even write 4 bytes at a time, given compiler that can support it. TurboC can't, but yeah, that's another problem. So we want to change that, and we do this by introducing a flag First of all, we will introduce a flag. We call the flag modex. And I'm gonna set it right away to 1. So we can switch back and forth between the implementations. And what this flag will do is, instead of calling copy to page, if modex is set, we'll copy a different, call a different routine. And this routine will be very similar to the copy to page, at least on the surface. And we will call this function blit to page. It will take exactly the same arguments. It will semantically function the same, but it will be much faster. Okay, we will implement this function here somewhere. Let's see where the copy to page routine is here. Let's just put it below the copy to page routine. And let's see, did I already define it? Yes, blit to page is already here, so I probably already put a stub in there. So let's search for blit to page. Here it is. Yeah, this is a stub. And when we look at this, and I have to spy on my notes so I don't make too many mistakes. The idea here is as follows. We basically want to iterate over all the pages that we have. So we will have sorry, fingers got messed up. We will have a page variable, and it goes from 0 to 4 or less than 4. All right, so we will go through all 4 video pages of the VGA. And we will select only once the correct page that we want to write to. So we write to the sequence controller index register, that we want to write to the map mask, the mask map register, and then to the data register we write the usual stuff, and the usual stuff is normally P and 3. This selects the correct page, and we left shift the 1 because 2 to the power of P is the mask that we want to select. However, we can adjust with an offset here, and we need to take this into account. So we will actually take P plus X so that the right page is taken. As you remember, every 4th pixel in the mode X memory space belongs to the same plane. So if we start at the pixel number 0, we are fine with just doing P and 3, but if we start at pixel number 1, then we need to take the next page. So we need to calculate P plus 1 and then mask with the 3. Okay, that should do it. Need to close the parentheses. So we definitely need some kind of counter variable here. It's enough if this is a byte. And next up, what else do we need to do? We need to calculate where in the source bitmap we have to start. And we call that the bitmap offset. And this will be the plane that we are currently looking at, because the memory that we will be blitting will be stored in such a way that it's exactly like the mode X memory. So also in this page-wise fashion, we won't have continuous pixels as in the mode 13 case or as we load GIFs right now, but we will put them in memory, in the main memory, exactly as mode X wants it. So we need to calculate an offset with a page included. And this will be the page number times width times height, because that's the size. But of course, every page is of width divided by 4, because it contains only 1/4 of the pixels. So we need a couple of more variables. We need a double word for the bitmap offset, and we already have the width and height as a parameter. That's fine. The same goes for the screen offset. Here we will take the input y times the current VGA width, which should be 320 in our case here, plus the x coordinate that we're shifting and the p page. And all that divided by 4 again. I can also write divide by 4. That doesn't matter so much. So this here will be slightly faster if the compiler is a bit stupid, but we can also write this. This won't make much of a difference. Okay, now we have the bitmap and screen offset, and then we need to we can now copy whole lines, and that's the main advantage. We only need to do the port writing once per page, and then we can do efficient memory copying per line. So we take some iterator variable j, doesn't matter what its name is, and this runs up to the height of the copied stuff, and we increment it. We probably should also introduce it up here, and we should also introduce the screen offset. And did I forget anything? No, I think this looks pretty okay. And then we actually do the mem copy. The mem copy takes the destination pointer, which is the VGA memory. We defined that already in the previous episodes. Plus whatever page we selected up here. This is the page offset basically for the screen, plus the calculated screen offset. And yeah, let's break this so we can read it better. Then comes the source pointer. We're taking it from the source image, and we add the bitmap offset, we called it, to that. That's fine. And how wide is our line? Our line is width divided by 4. Oh, that's great. This is our memcopy call. It looks maybe a bit weird indented like this, but I like to do it this way because then you have one parameter per line. If the parameters are calculated, this is, I think, much easier to read. Okay, now we have to increment our bitmap offset, because after every line we will increment it by width divided by 4. This is the length of the line. And the same for the screen offset. Here we take the VGA width divided by 4. Okay, this in theory is already our blit to page. Does it compile? One warning, which is fine because I already have a different stub in here that we will take a look at in 1 second. And then it should work. Let's see what happens. But nothing happens. Okay. Yeah, here we are. So this looks like this. And this is actually what the memory more or less looks like when put into the planes. So everything is shifted and multiplied by 4, and it looks totally weird. Because the memory is not yet in the modex format in the main memory, and we just copy it over. So that's wrong. We need to change how we plot the pixels in the GIF loading routine, obviously. So, and the actual error that we just had was that TurboC had a crazy thought. I wrote the wrong variable here, I instead of j, and it didn't compile at all, but also didn't give me an error. That's weird. Sometimes Tobusi does this, then you have to restart it and it will recover. Everything's fine now. So let's go to the GIF. First to the GIF header. Let's say we want the load GIF to also know about storing in mode X. So I will give it a mode X variable. I will change the main game function to also pass it to, here we're not using spaces, okay, I'm taking it out. So we pass it to the load GIF routine that it can plot the pixels in a different way. Yeah. Where is load GIF? Let's find load GIF. Load GIF is here. We pass it the mode X flag. And then we need to look at where the decoder is. And I think I already added. No, not here. I need to look at the decoder structure, which is right here at the top. Right here at the top. No, we didn't add it yet. We will also add the mode X flag to this. Then we find the load GIF function, and wherever the decoder is mallocked, we can already set this. Decoder mode X equals mode X, because then we can use it in the next pixel routine. The next pixel routine, if you remember, and if you don't, you should definitely check out my video on loading GIFs and not GIFs. I will put a index card in the top corner if possible. The next pixel routine unpacks the next pixel that was decoded from the GIF. It's basically a fancy plotting routine. It handles interlacing as well and stuff like that. But mainly we want to simply change it. We want to also have it use mode X. No, we don't want to put it here. We put it in the decoder state, which is absolutely much better. So if the decoder mode X is set, we do something different from the typical setting the pixel. But what actually do we do? Now it becomes a bit more complicated, but not that much. First of all, we need to deal with the planes. So we will calculate the plane. The plane is very simple, actually. The decoder x coordinate contains the current x coordinate. And as we all know, x modulo 4 gives us the plane, which is how we set pixels in mode X in the first place. And the actual x coordinate that we have in memory is the decoder x variable divided by 4, because every plane contains only 1/4 of the pixels. So now we have the plane and the new x coordinate. Then we can compute the offset into memory. And the offset is again the plane that we calculated times the size of the x-axis of our image, again divided by 4 due to the width of one line in mode X, times the size in dimension y of the whole image that we're decoding. And that's actually it. So we need to define x1 and offset up here. And we need to set the pixel. But this is nothing hard anymore. So this will look just like below. It will be the color masked to 255. So because it's an integer, it could be bigger. Shouldn't, but could be. And again, we take the image data pointer. We add to it the offset that we calculated, which gives us the pointer into the page. Plus, of course, we need to take the y coordinate times the size of the width of the image divided by 4 plus our coordinate x1. Yeah, so the offset is just the plain offset, and the part behind that is the calculated pixel offset, which is the typical formula, which is usually simply y-coordinate times width plus x, and this time we have y-coordinate times corrected width plus corrected x-coordinate. And that's it. That should, in theory, already work. We get 6 errors. Plane isn't, of course, defined because I forgot that. So let's make that a word as well. And we mistyped decoder. And what else? Oh yeah, we should probably put a semicolon there. Fixing errors as we go. Declaration syntax error. Okay, there should be an else and a curly brace. And it looks much better. Now have a look. Let's start it. Load the 4 images. And it's fast. This is 4 frames per second. And just for giggles, we can crank it up to the maximum. And then we can compare. Let's just take out the delay. Now it's just limited by the page flip, which syncs to... Okay, again, it doesn't compile. So I have to do all the compilation steps manually. Now it just syncs to the vertical refresh, which is 70 Hertz, even on the simulated DOSBox, and will be crazy fast. As you can see, it's crazy fast. This is how fast we can copy, at least on DOSBox. We will test it in a minute on a real 386 PC. And now, just for giggles, we change the mode X variable to 0, and then you see the raw performance of the set pixel routine. And here we go. And this is the raw performance of the set pixel routine. As you can see, this is roughly 2 orders of magnitudes slower. I think this is 1 frame per second versus 100 frames per second or something like that. So now we have some pixel blitting routine, which is actually useful, and yeah, I think this is extremely helpful in making the game actually work in a meaningful way. So what did we do? We tweaked the load-give routine so that it actually loads the pixels into main memory in the same way that the VGA actually requires them. Then we tweaked or created a blit to page routine, which only has to do the port commands 4 times for every plane once, and then we copy the data for each plane line by line, because this is what works. It doesn't matter what the size of the image is, as long as it's smaller than the VGA screen. And this is extremely fast, as you can see, and this we can use in the next episodes to build actual running sprites and fast game action. And now I'll switch to the 386 and we have a look how it performs, if it works at all on that machine. I hope so. Yeah, so let's turn the 386 on. Okay, here we are on the real machine, and yeah, let's just fire it up. And let's take a look. So the loading is slower because I tuned DOSBox to be a bit more faster than the 386, but that's okay. And as you can see, it's crazy fast as well. And this is on a lowly ISA bus, no less, which is 16-bit and only like, I don't know, 8 megahertz or something. So you get at most something like, I don't know, 16 megabytes per second maybe, if you're lucky, probably much less. So this is actually pretty impressive that the VGA can push this much using modex and some slightly clever programming techniques. Okay, I hope you don't get a seizure from this. I'm gonna stop this now. And yeah, let's have another look. So I hope you learned something. This is definitely something that we can build on for our progress in this little gaming thing. And I hope to see you soon. Please share, like, and definitely subscribe if you want to. And leave a like or a dislike. Leave a comment, let's have a little discussion. You can also post some comments on what I should cover in the future. I can only make like 1 or 2 videos of these every month. so far, because time is very limited. But maybe in the future we can ramp this up. So yeah, leave a comment and see you next time. Goodbye.